This lesson is going to get us started on slope fields. We have seen it a little bit throughout Chapter 6. I introduced it and I said we would definitely come back later. This is a question that is tested on the AP exam. Now, normally in class when I start this, we are going to spend a couple days on it. I give you guys a packet, and in the packet it has the coordinate planes drawn out like this with these little points on them. Unfortunately, since if you wish to print this out, you can. If not, just go grab a sheet of graph paper and draw coordinate planes of this size, and we can fill this in as we go. You're definitely going to need a ruler too, so go ahead and pause the video and make sure you have that. All right, so when we looked in the book at some problems having slope fields, we saw like little line segments all over the place. We even graphed this on the calculator, which I'll show you again in a moment. But a slope field has all these little line segments over it because it's a field or an arrangement of all the slopes of the tangent line. So at each little point, we're just looking at a little line segment representing the slope that's there. So in this packet, I just sort of copied one problem at a time here. So we're going to do 3 problems together. And then I'll give you numbers 4, 5, and 6, and then tomorrow I'll have the rest of the packet scanned in and copied for you here. So we're going to look at this algebraically and graphically. The slope fields tie in with differential equations. Slope fields are just showing us all the general solutions. When we have that plus c, it's showing us all the possibilities, and then when we get more specific, we'll have that. So this will also be good practice with solving differential equations. All right, so if we take a look at number 1, we're given that dy over dx is equal to -2. So first I'm going to solve this algebraically. I want you guys to go ahead and pause this, and you go through. This is nothing new right now. Just figure out a general solution. Just stop there. There's no initial condition. So what we could do is not really a need to separate variables here because we don't have variables really, but we can have just the dy is equal to -2 dx, or we could start with saying y prime is equal to -2, therefore y is going to equal the integral of -2, and then don't forget to put that dx. So this is 2 different ways we could do this, and then going back we could take the integral of each side. But the way I have this over here on the left, the dx is already there. If you forget to put the dx over here on the right, then you're going to miss a point for forgetting that. So over here, this is where we're getting the y is equal to -2x. Actually, we could say before we do anything else, the c, I know it's going to go away at the end, but y plus c1, -2x plus a second constant, and then y is equal to -2x. And then subtracting c1 from c2 will just give us our c. Over here, we'll get the same thing. Y is equal to -2x plus a c. So again, this is our general solution. Graphically, though, and again, when you go to draw the coordinate plane here, notice I'm only going 3 to the right, 3 up, 3 to the left, and 3 down, so you don't need to make it any larger than that. But what this is saying is at any x value, so let's just start with x equals 0, all my slopes, because right now this dy over dx, that is the slope of the tangent line, is -2. And because there's no variable here, it's -2 always or everywhere. So if I start at x equals 0, try to use your ruler as best you can. I need to draw a little line segment. I'm starting at the very bottom here at 0, -3. The slope would be a -2. So I'm going to go back up to this point and kind of imagine, I'm not going to use a ruler here, but I'm going to make a little line segment that looks like this because it looks like it has a slope of -2. If I go up here, I'm kind of matching it up with this point. So again, a slope of -2. All right, so just at the bottom of that column, I'm writing that I have a slope of -2. When I go over to x equals 1, again, I'm kind of lining it up with this point, so I could say we have a slope of -2 here. And for some of these, it does get a little tedious. A lot of times on the AP exam, they may only give you about 6 or 8 points that you have to do this, but for right now, we are going to fill this all in. So as best you can, again, in this column, make those little line segments here. We have a slope of -2. When x equals 2, we'll do the same. As long as it's close enough, it's going to count. If it's too drastically off, just be very careful. So again, we're going to go slopes of -2 here. And even over at the left, when x is equal to -1, we have a slope of -2. X is -2 and -3, we have the same. So when we go to look on the calculator, we're going to see this. This is where we're getting all of these little line segments here. So all of these lines have a slope of -2. So on your calculators, if you guys go ahead and grab that, we're going to go to a graphs page. And then go to menu 3 and go down to, on here it's number 7, but on my actual handheld calculator it's 8. You're just looking for that diff EQ differential equation. Now remember, what it's going to show you here is in one box you have a y1, and then it actually has a prime outside of the box that's there. So this is where you just want to type in -2. We don't have to type in anything else. And if you notice, this is what you should get. So because of the orientation of the window here, that looks a little more slanted than what we're looking at, but this is what we ended up typing in as well. Now, if we had a specific solution, let's say that C ended up equaling a 1, then we would go right up here. And then if you notice, I'm just going to draw a line in here that if we were to go up to and over 1, we would have something maybe like right here. So looking at this line, an example. So if C happened to be a 1, we would have it going through 1. If we were looking at, let's say, C is equal to a -1, we would have something that looks like this. So we could see that all of these slopes look like they're going parallel to all these little slope lines in the slope field here. So this is how we would get our specific solution. So even if it's not going through an initial condition, we could change the value of C, but this is the idea. So these would be specific solutions that we're filling in here. All right, so nice way to check on the calculator as well. All right, so if we take a look at number 2, again, go ahead and draw another coordinate plane here. Here we're going to make a table of values because it's not a constant. Our derivative is x minus 1. So we're going to make a table of x values, and then here we're going to have, almost like when we went back to first starting to look at graphs of derivatives, dy over dx is equal to x minus 1. All right, so if you notice here, I'm going from, we'll start at -3 and go to +3, because these are all the x values we're looking at. So if dy over dx is equal to x minus 1, -3 minus 1 will give us a -4. -2 minus 1 will give us a -3. -1 minus 1 will give us a -2. 0 minus 1 is -1. 1 minus 1 is 0. 2 minus 1 1, and then 3 minus 1 will give us 2. So all of these are the slopes at each point. So if I'm looking here at x equals -3, I'm going to have slopes of -4. So again, they're going to be pretty steep. We're just going to try to draw this as accurately as possible. So let's start up here. If I were to count down 1, 2, 3, 4, and over 1 and try to connect this back, it's going to be pretty steep looking like this. Again, we're just trying to draw it as best we can, but that would be a slope of -4. After that, we would have a slope of -3. Then we would have -2. At 0, we would have a -1. So again, I'm kind of lining it up with this just to show. You could use your ruler. At 1, we're going to have 0, so that's the easiest one to draw in here. At 2, we're going to have a slope of 1, so now it's positive, so I'm kind of matching it up with this. And then at 3, we're going to have a slope of positive 2, so I'm going to try to match it up, like counting up here, up 2 over 1, so we're looking like this. All right, so if we were to take a look here, notice this derivative is linear. And remember, when we take a derivative of something, our function goes down a degree. So that means if our derivative is linear, our function should be what, guys? And if you're thinking quadratic, that's correct. So we'll just put here our function y is going to be quadratic. And if we were to follow the slope field here, let's say we were to start over here on the green and sort of come down. Notice at 0 it turns, so that's where we would have a max or min. So we could kind of show we're coming down like this, and then we start to go back up. So we do have something that looks very similar to a parabola is what I'm drawing in here. So that's graphically just showing this. Now algebraically, if we have again, algebraically is everything we were doing before. So dy over dx is equal to x minus 1. This is where we want to definitely show separation of variables. So we're going to say just dy equals x minus 1 dx, and we'll take the integral of each side. So we're going to get y plus a constant is going to equal x squared over 2 minus x plus a constant. So then y is going to equal 1/2 x squared minus x plus the constant. So this would match, again, if you were to check on your calculator and type in the derivative here. So what's even nice is go ahead and do that. Go back to, I don't have it up on here, but if you go back to your differential equations, that menu 3 option, type in x minus 1. Then carefully you could hit tab, go back and just change it to a function, and then type in 1/2 x squared minus x, and then actually pick a value for c, and you're going to see it show up rather nicely going between the little line segments here for the slope field. So whatever value you choose for c, it's going to fit real nicely there. But again, this is our general solution for the differential equation, and we have a slope field to match. All right, take a close look at 3, kind of look to see what looks a little different than the last 2 examples we did. We're going to make another table. But in this case, notice that in number 2 we had an x. This time we have a y. So we're going to make a table of our y values and then our dy over dx, which is equal to y. So what this means, notice my y values now, I'm going to count going up and down, and I still go from -3 up to +3. Now, if dy over dx is equal to y, then if y is -3, my slope, my derivative, is also -3 if it's -2, so these all match. But now I'm going across the rows here, so if I'm down here at -3, every little mark going across horizontally is going to have a slope of -3. So again, I'm going to start right here. If I were to count up 3 and over 1, I would get a nice sort of idea of how slanted to make this. And then at y equals -2, all my slopes are -2. At -1, all of my slopes are -1. At 0, all of my slopes are 0. 1, all of my slopes are 1. And that's y equals 1. At 2, all of my slopes are positive 2. And then at 3, all of my slopes are positive 3. So if I start down here, go up 3 over 1, we're kind of matching it here. All right, so there would be my slope field. Now, if we take a look before we try this algebraically, notice if we were to start off here along the x-axis, we're kind of straightening out here, and then we start to kind of lift off here. But if we started below, notice we would start to go down. So this would actually give us, if we did a separation of variables, which go ahead and start, we're going to see within our first step what we should expect to show up when we go to solve this. And I'll come back to that picture. So if we wanted to start with the separation of variables, we would have what? dy over y equals dx. Then this becomes the integral of 1 over y dy equals the integral of dx. And as soon as we take the integral of 1 over y, what are we going to end up with, guys? Natural log. And if you remember what the natural log looks like graphically, or what we're going to get involved here is going to be a function of e. And if you remember what the graph of y equals e to the x looks like, before we continue here, doesn't it start to have a horizontal asymptote at x equals, or y equals 0 here? Stay up here on the graph. So it might start to take off something like this, if I were to draw that a little better. But let's take a look here. So we're going to get the natural log of really the absolute value of y plus a constant is going to equal x plus another constant. So then the natural log of the absolute value of y is equal to x plus some constant here. But now we need to use a base of e on each side. And we've seen this plenty of times, so we're going to get the absolute value of y. This becomes e to the x times e to the c, and I'm just going to use this as a. So then absolute value of y is going to equal a times e to the x. But because it's absolute value, we're getting that y is equal to positive a times e to the x, and that's going to match something that I just drew in there. Or y is going to equal the opposite of a times e to the x, which could give us this bottom part if we were to start here and kind of go down in this direction. So that's why it helps to have that absolute value to show we have two separate general solutions depending if they're not going to be connected here. So these are our general solutions again, matching that slope field. So again, this is just